Welcome back, everybody. So today we're going to kick off our middle school problem solving series with one of the classics. So really, everybody should know how to solve this kind of problem. So the problem is, find the sum of the counting numbers from 1 to 25 inclusive. So in other words, if the sum equals 1 plus 2 plus 3 all the way up to 25, we want to find the value of the sum. So I'm enlisting the help of my son, Kyle.
Hi.
Who's a real math expert. Kyle, how old are you?
8.
And so what grade are you finishing up?
I'm finishing up 2nd grade.
So don't let his diminutive size fool you. This kid's a real math wizard. He's going to really be able to help me out.
And there was actually a story about a math prodigy named Carl Friedrich Gauss. And he was born April 30th, 1777.
Hey, that's the same birthday as me. Not the 1777, but the April 30th.
Oh, and he had a very lazy teacher, and he was only 7 or 8, so not much older than me. And he had a lazy teacher, and he wanted to take a break and maybe get some coffee and take a slight nap. And so he gave them the problem and said, find the sum from 1 to 100. And just as he was walking out the door, Carl Friedrich Gauss raised his hand and said, it is 5,050 precisely. And the teacher was astonished because they thought it would take them forever.
I'm sure he was a little bit frustrated too. Now he didn't get to take the day off. Now he had to go back to work and start teaching again.
He probably was.
That's a really cool story. Man, I wonder how Gauss was able to calculate the answer so fast.
And we can do it too.
Oh, we can do it too?
Yeah.
All right.
So
how do we do it?
Write the sum forward.
Want me to write the sum down going forward. Okay. Got it.
Now right below that, write the sum going entirely backwards.
Okay. Got it.
Step 3, add the terms together.
I'm going to add up every one of the terms, huh? The first one's easy. That's just 26. The next one, 26.
Third one.
26 again? Oh my goodness. Guess what? I think every single one of these are going to be exactly the same number, 26. That's amazing.
And how much numbers do you have?
Well, let me see. I've got a list here, starting with 1 and going up to 25, so that must be 25 terms.
And you probably should know that multiplication is repetitive addition, and we have 26 25 times, 26 times 25, but we have 2 lists, so we have to divide that by 2.
Gotcha. I'm following you. So we got 26 times 25 divided by 22. So the sum
By 2.
of each of our terms times 25 terms divided by 2, because we've got 2 lists instead of 1. Completely makes sense. Well, I'll start off, make it a little bit easier by taking 26 divided by 2.
Which is 13.
That gives me 13, so I have 13 times 25. And that'll be my sum. And so let me multiply that out. And that is going to give me 325. So the sum of the counting numbers from 1 to 25 inclusive is 325. Well, that's a pretty cool trick. I can see how we can apply that trick if I'm adding the numbers from 1 to any number above there, right? You just write the sum going forward, write the sum going backwards. The sum of the terms will always be the same. So I take that sum times how many terms that I have, divide by 2, and I'm always good to go.
And now we have a follow-up problem.
So here's our follow-up problem.
Find the sum of the first 25 even counting numbers from 2 to 50 inclusive. In other words, if s equals 2 plus 4 plus 6 plus dot 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 plus 48 plus 50,
Okay, so we're going to try to find this sum now. 2 plus 4 plus 6 all the way up to 50. So how do you think we should approach this problem, Kyle? This doesn't look exactly like the same problem that we used with Gauss's trick. So it doesn't start at 1, and it's not going up by 1. So I'm a little bit confused on how we should proceed.
But does it have any common factors?
Well, it's the even numbers, so it certainly has a common factor of 2.
Then what happens if you factor out 2?
All right, let me try that. Let me factor out the 2. And that leaves me with 1 plus 2 plus 3 plus 24 plus 25.
And does that look like the exact same problem we had over in the first problem?
Well, yes it does. So that actually is exactly the same problem that we've just gotten done solving. So that leads me to a very interesting problem-solving strategy. If we can transform the problem into a problem that we know how to solve, then we can take a problem that's unfamiliar and actually make it into a problem that's familiar, right?
Okay.
So if we go back to the previous problem, we can apply Gauss's trick to the same thing, but we just got done doing that, right? And we found out back here that when we use Gauss's trick for the sum of the numbers from 1 to 25, that we get the answer 325, right?
Mm-hmm.
So we can just plug that in here now. So we've got 2
times 325,
times 325.
which we know is 650.
There we go. So now we've got the sum of the first 25 even counting numbers from 2 to 50 is 650. And we were able to get it using exactly the same Gauss's trick that we had applied before.
But what if a kid has that same problem, but they say find the numbers from 1 to 1,000?
Wow, that would be a big long sum to write out, man. How about if they asked you for the sum of 1 to 1,000,000 going up by ones?
That'd be even bigger. Now, people wouldn't want to write out 1 plus 2 plus 3 plus 4 all the way to 1,000,000.
No, so it'd be really nice if we could A, prove that Gauss's trick works for any sum from 1 to any number n,
and find a formula that kids can easily come along with if they ever do find a problem that's way harder than this.
Yeah, it would be nice to have a formula, wouldn't it? So we didn't have to write this out every time. Well, let's see if we can do that. We'll start off the same way that we had started off with
Except
Gauss's trick.
We're going to write 1 plus 2 all the way to n.
We won't set the top end of the number. We'll just make it some number n that we don't know what it is yet, right?
Because you can just plug in any number for that. 1,000,000, 1,000, 5,000, any number you can have. Now, we can use, as we did in the first problem, write it backwards.
Right. So I'll start off with 1, writing it going forward in this direction. This one will be n minus 2. This one will be n minus 1.
That'll be n.
This one will be n.
And then we just add them up like we did in the last problem. And then we get...
This is n plus 1. This is n plus 1. So now exactly the same thing happens. They all come out to be n plus 1. And now I see a little bit why it always comes out to be n plus 1, right? So these are always going up by 1, but when I write it going backwards, they always go down by 1, right? So when this one increases by 1, this next term on the bottom series decreases by 1, so the sum is always going to be the same, right? So now my sum is n plus 1. How many terms do I have this time?
You have n terms.
I have n terms. So now I'm going to do n, number of terms, times the sum of those terms, n plus 1. But what do I got to do?
You have to divide by 2 since you have 2 lists.
I got to divide it by 2 since I brought an extra list into it, right?
And you can always make it easier because there's one number and another number, so one's going to be even, one's going to be odd, so then you can always divide any number. It can be n or n plus 1. You can just divide by 2. If n was 2, you use n and simplify. If n plus 1 is 2, then you use simplification.
Pretty nice. So there's our formula. So now we have a general formula that we can apply for any sum of numbers from 1 to n, going up by ones.
It works.
And we proved that it works. So that's pretty nice. So let's try this out for the problem that we just got done solving. So we wanted the sum of the numbers from 1 to 25 inclusive. So the terms is 25, so we're going up to 25, so we have 25 times 26 divided by 2, and sure enough, that's our 25 times 13, and that equals
325.
325.
And can we do one more thing?
Sure.
How about let's prove that Gauss was right. Let's prove that the sum from 1 to 100 is 5,050.
Oh, that's a great idea. So to do that one, we're going up from 1 to 100 by 1, so n is 100. So we have 100 times 101 divided by 2. So we'll do what Kyle said. We'll always take the even one, because this is two consecutive integers, so one's even, one's odd. We'll take the even one, and we'll divide that out by 2.
So then
And
we
so
have
now
50
we have
times 101,
50 times 101.
which of course is 5,050.
Yeah, let's show that though. Let's rewrite this as 50 times 100 plus 1.
And then
Now
we
we'll
have
apply
50
distributive. 50 times 100 is 5,000.
plus 50
plus
times 1,
50.
which is 50.
Is 5,050. So I think you're right, Kyle. I think that's probably the method that Carl Friedrich Gauss used in order to prove, or in order to get his answer so fast with his teacher. So he had either already figured out the formula, or he just did a sum forwards and backwards and was able to get it real quick, just like that, right? And so one other thing, so if we wanted to basically calculate the sum of the even integers like we did before, so let's say we have 2 plus 4 plus 6 plus going up to 2n, where we want the sum of the even integers, we're going to do what we did before. We're going to factor out the 2, and now we have the sum 1 plus 2 plus going up to n, and now we'll plug our formula in that we just calculated. So we got 2 times n plus 1 over 2. The 2's cancel out,
The 2's cancel out.
leaving me with just n times n plus 1. And so that's the sum of the first even integers. Now the key thing about this formula, though, is you have to remember this goes up to 2n, so if it's like 2 to 50, n is actually half that, right? So n is the number of terms, which is 25. So if I just take 25 times 26, that'll be the sum of those formulas, right? So now what we want to do is we just want to show you one more proof. And for that, this is actually a geometric proof. And so what we've got here,
So we're going into GeoGebra.
yep, so we'll go into GeoGebra and we'll just do a geometric proof. So let's say we want to find the sum of the numbers from 1 to 10. So you can see we have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. And you can see that this makes it triangular, and that's part of the reason why all of the numbers that we get by going n times n plus 1 over 2 are called the triangular numbers. So what we want to do is we want to do something very similar. We want to take a copy of this triangle.
Which is just how we made the list, forwards and backwards.
Yep, we want to take a copy and we want to reflect that about the line shown on the screen. And so once we reflect it, then we actually want to put those two pieces together, and you can see that it makes a rectangle. Well, what's the dimensions of that rectangle? Well, if you see going across, we just have n, whatever our number was. So in this case, our n was 10, so we have 10 cubes going across.
And how much do you have in length?
How much do we have in the length? Well, we have 10 plus this extra one down here, right?
AKA n plus 1.
N plus 1. So in this case, it's 11, but if we took a general triangle, this side would be n, the length would be n plus 1, so we would have n times n plus 1, and we ended up with 2 of our triangles instead of just 1, so it'd
So
be
we have
n
to divide by 2.
times n plus 1 over 2. So we see that explicitly with our formula here. So we've got half of the area of our rectangle, and so our sides are n and n plus 1, so we have n times n plus 1 over 2. So that's kind of a nice geometric proof and an introduction to the triangular numbers as well. That kind of gives you another proof of the formula for Gauss's trick. So, thanks a lot for the help, Kyle. You did an awesome job. Pat yourself on the back, and we will see you guys again next time.
Make sure you subscribe.